Hello, everybody. I'm delighted to be here, and thank you very much for letting me speak. This talk is something of an overview, and it is based upon a gallery, an exhibit at the Air and Space Museum that I curated in the late 1990s. And opened in 2001, especially poignant date, September 11th, 2001. New Tools, New Universes encompasses, of course, a very large scope. And the general idea is as we acquire new tools of perception, we realize that the universe isn't what we thought it was. And of course, the logical progression is starting with the eye, and then the eye in the telescope, confirming Copernican cosmology, then adding photography, answers Herschel's questions about what are the nebulae. Sidereal universe becomes a universe of galaxies. We have spectroscopy then, plus photography, plus telescope, and that leads us to dynamic things. We have interferometry, that allows us to go beyond the atmospheric limits. We have electroscopy and the detection of high energy particles. There is then radio, and then finally the digital universe, which is now being referred to as multi-messenger astronomy. Now this is based upon a gallery, as I mentioned, that contains a number of instruments, and what I'm interested in now is your reaction to the instruments that we chose back in the 90s to represent these stages. The visitor walks in here, first encounters the universe according to the eye, and then according to the telescope, to photography, spectroscopy, and all of this is additive, and finally into the digital universe, which takes up 60% of the gallery, dealing with the modern views of the universe. In each one of them, you can see the instruments that we highlight. And again, I'll be very interested in reaction to this. Now, as a historiographical background, I always like to use Martin Harwitz's Cosmic Discovery, and I'm delighted and honored that he's with us today. Repeatedly, discoveries of novel cosmic phenomena have been made by men and women who looked at the universe with new instruments and came to see it from a fresh perspective. And that new instruments could be observational, experimental, or theoretical. I will be talking about the observational instruments here. Among many views, of course, we start with the eye. And in the first room, we look at the eye, the universe according to the eye, with astrolabes and a little interactive on how one can use an astrolabe. And then we have all sorts of murals depicting those universes for our visitors. The astrolabes get more and more sophisticated over time, and ending the visual era with Tycho's armillary sphere, with which, of course, various Aristotelian assumptions were being tested by Kepler and others. The eye plus the telescope then revolutionizes astronomy at the time and allows us to begin to, as Galileo said, use images as argument. We developed the telescope and the eye in the next section, ending with Herschel's 20-foot telescope that has been on loan to us very generously by the National Maritime Museum in England. I should point out that most of the instruments in the gallery are in our collection, but we have an active loan program. We loan out and we bring in instruments of significance. This is the original tube from Herschel's telescope, and we have the last mirror that he and his son John made in 1820. Now we depict through audio conversations between Caroline Herschel here in the window and William as she helps him systematically mapped the universe with various disciplined assumptions. And the importance of this work is that he found a statistical anomaly. They found it, I should say, and that is that the nebulous objects in the universe had a completely different distribution than the stars. And Herschel asked the question, what does that mean? Are they part of our universe, or are they separate sidereal universes? Okay, we move on then to photography and the various values of photography through integration time. Of course, you can see more and more and more of an object. There is a certain presumed objectivity to photography. Omar Nassim, I think, has made some very interesting comments about the question of objectivity in observing by hand, but then with the photographic revolution, that entered a new stage. There are changes over time in space, and photography is very, very good at and far more objective than other forms, earlier forms of finding those changes. Now, changes in position is one thing, but changes in brightness are more subtle. And then finally, of course, there's mapping, being able to see far more than the eye can see and delineate structure. Now, with the time-dependent phenomena like variable stars, we have a blink comparator that's looking at a cluster of stars at two different times, and we demonstrate for the visitors that they can easily find stars that vary in brightness. Even though Henrietta Swan-Leavitt did not have a blink comparator, and she used a much more laborious technique of pairing positives and negatives of the Small Magellanic Cloud as seen at different times, of course, what she discovered was absolutely revolutionary in that these variables seem to vary as a function of their intrinsic brightnesses. And from that was developed the period luminosity relationship, one of the most important correlations established because it allowed for a much vaster distance scale. The first application of that was by Harlow Shapley, who looked for Cepheid variable stars in globular clusters, found that they centered on not the sun, but they centered on a bright portion of the galaxy. And in the galactocentric revolution of 1917, he displaced the sun from the center of the galaxy. Now, Shapley did this with the 60-inch telescope at Mount Wilson, and it really is to George Ellery Hale's credit that he built the largest telescope in the world 4 times. And the 60-inch was his second, and the 100-inch was his third. And with it, we display the Newtonian cage from it, courtesy of the Carnegie Institution in Washington. We depict Hubble observing with the Newtonian cage, and we present his discovery plate of finding a variable star in M31. And this, of course, gave us a new revolution, that an answer to Herschel, that those sidereal systems are definitely external to our own Milky Way and external to Shapley's galaxy, let's say. Now let's move on to spectroscopy, which is the next revolution. As we all know, spectroscopy, the application of spectroscopy to astronomy began in the late 19th century, and it was very qualitative, of course, equating color of the star to the kinds of lines that were seen. There was a little bit of chemistry underneath it, as Bill Brock has beautifully presented in the past, but as yet there was not quantitative work. It was not astrophysics, as some textbooks say. It was spectroscopic astronomy. But with it, you could, of course, detect empirically varying physical properties, but most importantly, motions. And since we use motions so much in the early delineation of the structure and dynamics of the sidereal system, we display the Mills spectrograph from the Lick Observatory in a trompe l'oeil. If you were standing over here, you would see it oriented to the tube of the telescope. And this, of course, also represents the application of photography to the spectroscopic process, something that was just beginning in the 1890s. And with it, Keeler and others at Lick Observatory showed just how powerful this technique was. And this design was duplicated at various observatories, including the Lowell Observatory. Now, spectroscopy, of course, then started being applied to all sorts of stuff. Slipher at Lowell, of course, had already shown that the spiral galaxies were moving at great velocity, much greater than the velocities of stars. But the first person to calibrate that, the velocities with distance, of course, was Edwin Hubble. And this is a refined variation of his first diagram, greatly reducing the scatter. But it made the point that there was a relationship between the distance and the recessional velocity of an object. Other people interpreted this as an expanding universe, as you well know, starting with Lemaitre and Lundmark and others, Erpich, and that developed as a dominant theme in the 1930s and 40s. Now, at that time, before that time, about in 1920, all these correlations that were being found, the period luminosity relationship, and then later on, of course, the redshift distance relationship, but also star streaming, the color magnitude diagrams, what we call the Hertzsprung-Russell diagram, all of these things started really making astronomers wonder, what did they mean and why are they happening? This ranges from both observational astronomers like Walter Adams at Mount Wilson and E.A. Milne in Cambridge. And the question was, do we know that these stars and these objects are really acting according to physical law? And physical law at that time were the radiation laws. This got to the point in 1920 when Arthur Eddington, in his retiring address to the British Association, said, you know, we have all of these relationships, but we don't know what they mean. And in order to determine if the stars really are behaving to the radiation laws, we have to have a test. And the test that he suggested was measuring the angular diameter of a star. And of course, that would be impossible given our atmosphere and its turbulence. But there was a way to get around that. And since the 1890s, A.A. Michelson, of course, had been using interferometry for many purposes and got the Nobel Prize as a result of it. But one of his long-term ideas was to measure the angular diameters of stars. He tested it on the moons of Jupiter in the 1890s. It worked beautifully, but it had to wait until there was a telescope big enough, and that was Hale's telescope, to build a beam big enough to be able to measure them. Now, the longer story behind this was that it was only with Eddington's prediction of Betelgeuse being 0.051 seconds of arc in angular diameter did they really know that the beam was big enough to make that measurement. This is one of the interesting serendipities that I've never been able to determine how it happened. Did Eddington know that the beam was being built? And I would love it if one of you could find Eddington's papers and answer that question. But then this demonstrated that stars act according to the physical law, and that stimulated, and why is it's not advancing? Oh heavens, what's going on here? Can somebody help me?
Matteo, can you tell something to...
I don't know, try to exit from your presentation and try to reopen it maybe.
Okay, I got it. But let me double check. Yes, this opened up the application of the physical laws of the Bohr theory and ionization theory to the applications of stars. And from there, we well know that out of it, using the wealth of spectroscopic. Okay, I'm getting some. Okay, I'm better. The wealth of spectroscopic data at Harvard, Cecilia Payne-Gaposchkin, by the early 20s, deduced that the atmospheres of stars were made primarily of hydrogen, and hydrogen was dominant in the universe. This was an extraordinarily radical thing to come up with, because Eddington's models, which were dominant at that time for how stars behave, required that there not be very much hydrogen. And that is really the story behind why there was resistance to her work. It had nothing to do with feminism. Henry Norris Russell rejected other determinations at the time, even by his close colleagues, that hydrogen was dominant. It took until 1939 in the work of Rupert Wilt to show that indeed it was. But here was the next revolution in astronomy. So we now have a hydrogen universe. It's expanding. It's got galaxies in it. What else is out there? Well, in the 1930s, the radio universe was discovered by people primarily interested in communications. And once it was discovered, of course, again, one would look for structure. That started in the 30s with small dishes, but it continued in the 50s with large interferometric arrays trying to better resolve that structure. And the thing that they found was that there were very intense radio sources with no optical counterparts, and they were star-like. And the natural point at that time, with optical astronomy being dominant, is that we really don't know what they were until we could look at them optically and figure out what they really were. And so the rush was on. Well, by the time that there was, of course, the 200-inch telescope was available, as was the most efficient, fastest spectrograph in the world, a f.5 solid Schmidt spectrograph that was stuck at the prime focus of the 200-inch. And with it, of course, the optical components were eventually found. Their positions had to be determined accurately by the interferometers, but the ones that really made a difference were the radio sources that were occulted by the moon during the motion of the moon among the stars. And with those positions, they were able to home in and find these optical objects that defied description, because they had lines in patterns that nobody could recognize, until Martin Schmidt realized that it was very highly redshifted hydrogen and other indications. And that high redshift, of course, was extremely important. Okay, we move now, continuing with the radio into the microwave, and we know Penzias and Wilson. What is the unique part of what Penzias and Wilson were doing? They were trying to get rid of or understand all sorts of noise, radio noise in the universe, so that Bell Labs could improve its satellite systems. So we decided to display what was significant about what they were doing. We display a pigeon trap. In fact, this is the pigeon trap that Wilson used to get rid of the pigeons that were depositing a white dielectric substance in the horn and causing radio noise. We then display it along with the Cointreau bottle that George Gamow modified to name Yellum or Ilum, primordial substance, when he and his colleagues calculated and predicted what the background radiation should be. So it goes from Gamow to Penzias and Wilson in this story. And then, of course, when you have a new universe detected, the whole idea is there structure to this universe. There have been a number of balloon-borne observations that indicated anisotropies, of course, and then some of those same people refined their instruments so they could fly on satellites. And John Mather and George Smoot and others at Goddard developed 3 instruments, FIRAS, Derby, and the differential microwave radiometer, to determine the structure in the primordial background radiation. This structure was at the instrumental limit of the devices, so the improvements, of course, came with WMAP and finally now with Planck. We have on display now the FIRAS and the differential microwave radiometer that were flown and tested on aircraft. They represent this. But now let's move from photons, beyond photons, to the particle universe, which was very, very nicely, I think, presented by Adele and Louisa, who offered, I think, in their presentations this morning, a very nice comprehensive overview of the world within which these instruments lived. Here is Victor Hess's electrometer or electroscope that he carried in a balloon to show that ionizing radiation increased with altitude. Here is a photocell from the neutrino detector, Kamiokande 2, that, in my opinion, really did start multi-messenger astronomy, not with gravitational waves, of course, that added to it, but really the first time that we had a particle detector and a optical detector looking and detecting the characteristics of a supernova 1987A. Well, let's now move on. There's a whole universe that can be talked about with particles, but let's now talk a little bit about changes in technology. And with solid state electronic detection and amplification, there was another revolution, not only in the ability to sense the entire electromagnetic spectrum from X-ray. Here are the HRI components. This is the breadboard that proved that the HRI on Chandra would work. This was actually his thesis of one of the Steve Murray's thesis. Here are the grids and the elements to the HRI. We also have Herb Friedman's X-ray detectors from the 1950s, with which he and others explored mainly solar X-ray. And then finally, we have one of the original CCDs from the first wide field planetary camera that flew on the Hubble Space Telescope. Now, the key behind CCDs and instruments like that, of course, is that they can provide a linear digital view of things, but that since they're digital, they can also be programmable, and programmable CCDs could be made to observe many, many objects in a very, very, very small amount of time in a particular field. And one of the first instruments that was built for that, what's called the Z machine, since it was dedicated to radio velocities, is on the 60-inch reflector at the Whipple Observatory. We collected the Z machine, and as you may know, from the Z machine came data that Margaret Geller and John Hukra and others analyzed with their students to show that the large-scale universe is not uniform, but is consistent with bubbles and voids. Margaret came from Princeton, where the ideas and the theory was being developed by Peebles and his group, and then she came to Harvard where the data was and produced the first maps, the early maps. And today, of course, we know of this strange filamentary structure, and we know that from Vera Rubin's work that I'll discuss in a moment, that the filaments are pretty much the indicators of where the dark matter is distributed, because the dark matter attracts the luminous matter, and so we can determine the structure of the dark matter this way. Why is it this way? This is, of course, one of the big questions, and it's always fun to contemplate. Well,
David,
of course,
David, sorry, your time is finished. I would like ask you to go to the conclusion, please, so we have some time for the discussion.
Okay. Well, the electronic detectors, of course, in Vera Rubin's hands, showed us that indeed galaxies behaved as rigid bodies, and there had to be invisible mass producing them, and this is the dark matter story. And then we also display the dark energy story using, I decided, the one key object, which was a mapping device called the Big Throughput Camera on the Blanco telescope in Chile that could find supernovae very distant in space that could then be analyzed by the great telescopes on Earth and in space, and thus extend the distance, the study of the Hubble constant, and decide on all the variations of is it expanding and will it contract or will it expand and continue to accelerate and expand? Of course, number 4 we found is the case. And that's about as far as I want to go, but for the future, we, of course, agree with Adele and Louisa that the LIGO was extremely important. And in our case, we had to ask, we can't collect LIGO, but what elements of LIGO can we collect? And we collected elements like a laser and like that mirror system that were designed to reduce noise. It was all about reducing noise. And so that's why we selected those 2 elements. And that's pretty much the same with the Event Horizon Telescope. You got all those radio telescopes around. How do they communicate? Well, they couldn't communicate in traditional ways of sending signals back and forth. The distances were too great. And so there was a very, very ingenious set of hard drives linked to atomic clocks that allowed them to be observations to be combined. We hope to be getting these instruments in the near future for the revision of the gallery. So if there's any time left for questions, I'll be very happy to yeah.
Thanks a lot, David. Okay, this fascinating overview of the instrumentations which allowed us to see new universe.
One point. I was waiting for the bell, and I didn't hear it.
Yeah, I mean, the bell was quite confusing. In fact, I don't know, maybe we should find another way because together with the bell, there is also the voices which are your voice. So maybe it's not the best way. You didn't hear them because
I'm sorry.
They should be more cleaned. Okay.
By the
way, we go to the question because otherwise there is no time left, and there is one question by. Sorry.
I'm sorry.
No problem. It's not your fault. I mean, there is a problem. There is a question by Scott Walter. So, can you elaborate on how spectroscopic astronomy differs from astrophysics?
The original application of spectroscopy to astronomy was all qualitative. There was, of course, the Balmer series, which showed that there was some order, but there were without a theoretical structure to appreciate why those lines appeared as they did, and really kept it qualitative and empirical, I should say, empirical study. In fact, most of the people who developed the correlations were observers, mapping type people, and they were not trained in anything that we would call modern physics. It had to be the importing of people who had physical background to astronomy, like Saha, and to make that difference.
So even Huggins' measurement of Doppler shift wouldn't count as astrophysics.
Scott, we don't hear you very well. Can you?
Well, in the case of the Doppler shift, of course, that is quantitative, and that was more provided information, of course, about the structure, the dynamical structure of the galaxy. And I will bow to that. That is a form of quantitative analysis that you might say can involve kinetic theory, as people tried to in the late 19th century to understand the dynamical structure of the universe. But it wasn't at the level of really revolutionizing our understanding of stars.
Okay, thanks a lot. There are 3 questions, but I don't think we will have time to do the 3 of them. I will read. Okay. Okay. What's the maybe Adele, you can ask your question yourself. What do you identify as the main? Okay, maybe Adele.
Yeah, it's okay. It's okay. Thank you for your beautiful overview, David. So, can you identify a special moment or a special observation or a special instrument in which you identify the emergence of astrophysics?
Well, it was really the measurement of Betelgeuse with the interferometer. That is when we knew that the radiation laws, and by that I mean Wien, Stefan, those laws applied to the stars, or I should say the stars behaved that way. It got even more quantitative with Cecilia Payne and her work. But her work was, as she said herself, the use of marginal line, the appearance of hydrogen across the Harvard spectrum was in fact a qualitative indication that hydrogen was highly dominant. She came up with some rough numbers of the actual abundances, but they were not confirmed for quite some time. She still should be credited with the first statement, and she should also be given credit for her audacious conclusions. But as you well know, she was told as a graduate student to say these certainly cannot be real. And that, of course, has sparked quite a bit of historical attention.
Okay, there are interesting questions by Paolo Brenni. I think that this will be the last one, but maybe Paolo, can you give your opinion yourself on voice, because it's more complicated. You're still muted. Oh. Okay. Yeah. Okay, maybe I read. I mean, there is a problem which maybe is technical. So I read what Paolo Brenni wrote. Why do you say that spectroscopic astronomy is not astrophysics? And then he wrote, but the first physical characteristics of stars were determined by spectrocs, which are of course related to this question. Can you reply to this question, and then maybe you can reply to the others within the chat?
Well, I thought I tried to answer it, and in fact, that is a very interesting point. When one looks at mechanisms of spectral classification and how they were organized, you can see that they were organized along a theory of stellar evolution, which was a speculation at that time that stars evolved out of nebulae and gradually heated. But the problem was that there was no clear relationship between, well, what kind of gas was involved. Henry Norris Russell, of course, assumed that stars behaved as ideal gases and contracted from being red giants to the point where they were on the main sequence when they, he thought, achieved a density where they no longer were ideal, and therefore they cooled upon further contraction. Well, that's wrong, as Eddington and Jeans showed later on using ionization theory. So I say that in a way, Russell was a transition figure using the correlations and speculating. Now, if you can call astrophysics speculation, that's fine. But I'm a bit purist about that in terms of contemporary. And I should say more, I'm more Whiggish than maybe most historians. And I do see this difference. It's also who is doing the work. As I mentioned, there were very, very few physicists interested in this work. And George Ellery Hale can be credited with trying to encourage physicists to join his laboratory at Mount Wilson, first at Yerkes, then at Mount Wilson, because he knew that physicists held the key to combining physical principles, physical experimental work with the observations at the telescope. He wasn't the first, of course. Norman Lockyer did the same thing, but Hale tried to spread it out. And again, it was through Hale that at least American astronomy became astrophysics. That may not satisfy everybody, but at least that's how I think.
Okay, thanks a lot, David. I think that we can leave it here.